So you can watch those. I might be able to have today's recording up today. I don't know. I'm trying the internet out here to see how well it is. I'm trying to upload my calculus lecture right now, and then we'll see how long it takes. Anyways, back to what we were talking about. Let's see, where did we end last time? We were talking about statements, right?
Right.
And now we finally get to start actually proving things.
Wait, is this us?
This is us.
Oh.
Yeah. It's a lot less than what was on my calculus board, so. And this is the vast majority of what we're covering today. Chapter 5 is a big one. Chapter 6 and 7 are both small. 7 you basically already covered, you just don't know because of how I cover logic. So, section 5 is on proof. And what is a proof? The proof that the author of the textbook, the definition that the author of the textbook likes to use for proof is it's a statement that you incontrovertibly show is true. In other words, no one can deny the truth of the statement. The way I like to say, what I like to call proof is, you prove a statement when you demonstrate it's impossible for it to be false. That's what I call proof. That's the author's verbiage if you're keeping up with the book, like you should. And then he has this discussion once again of the idea that having several examples of something being true does not make it true. We don't do what the scientists do. We don't look at several examples and then generalize from that example and say it must be true. Sometimes we guess that it might be true and we create what are called conjectures, but in general we know that that is not a valid way to prove. So, for example, I might try to prove the statement, all prime numbers are odd, and then I start testing examples. 3, yet 5, 7, 11, 13, 19, skip 17, 13, 19, etc. I could go on forever in this way. And I can find infinite examples of prime numbers that are odd. Does that mean that all prime numbers are odd? No, I just forgot one example, 2. Maybe for some reason I'm just not clever enough to think of 2 as an example. I wasn't able to come up with the right example. Now 2 might seem obvious, but maybe that number would have come way, way down the road. Maybe there was a really big number that turns out was prime that wasn't even. And I just couldn't think of it. Do you see what I'm saying? So just because you can't think of a case where it doesn't work isn't good enough for it to be true. Just because you try a bunch of examples and it happens to work doesn't make it true. 2 is a prime number, 2 is even. So this statement's not true. But if I would have started at 3 and started going forward testing every prime number, I would have found that they're all odd. So let's give you an idea of a conjecture that we've tested tons of examples of, but we still don't know whether it's true or false. It's the Goldbach Conjecture. It says that every even integer greater than 2 is the sum of 2 primes. And there's been computers cranking away on this, looking for one that doesn't work, all the way up. Let's just see it in action to make sure you understand it. So every even integer that's greater than 2, so we start at 4, 6, 8, etc.
So basically, an odd plus an odd equals an even every time.
Not that. It's not that I can write an even integer as 2 odds, it's that I can write an even integer as 2 primes.
Okay.
Does that make sense?
Yeah.
So we've had computers cranking away on this, testing and testing and testing numbers, and we still don't know if there's a case where it doesn't work. So there's mathematicians trying to prove this true. They still don't know if it's true or false. And there's computers cranking away trying to find a case where it doesn't work. But all the cases that they tested so far, it works. Because if they found one case that didn't work, then we know this is false, right? So if they haven't found a case where this is false, there's computers cranking away. And to show you exactly what it means, let's look at the first few even integers so you can see it in action. 4 equals 2 plus 2. Those are both prime. 6 equals 3 plus 3. Those are both prime. 8 equals 5 plus 3. Those are both prime. 10 equals 5 plus 5. Prime. 12 equals 7 plus 5. Prime. 14 equals 7 plus 7. Prime. 16 equals 11 plus 5. Prime. 18 equals 13 plus 5. Prime. 20 equals 17 plus 3. Prime. You can continue on your merry way, coming up with these primes that sum to numbers, and I'm sure that computers have gotten well to massive, massive numbers, and they've still been able to do it every time. So that's the idea of a conjecture. When we have several examples of something working and we're pretty sure it's true, but we don't have a proof for it yet, we call that a conjecture, not a theorem. Good? With what a conjecture is? Alright, so now let's start an actual proof. Now, every theorem that you try to prove in this class, every statement that you try to prove, can be reworded or reformatted into an if-then statement. Let's look at an example. The sum of two even integers is even. So the first step in systematically trying to come up with a way to prove these things is to break the statement up into an if-then statement. And it's also useful to create variables when you write it in an if-then statement so that you can reference them throughout your proof. So the sum of two even integers is even, rewriting that as an if-then statement, we have right here. If x and y are even integers, then x plus y is even. You see how that captures the exact same information as this statement? Pick any two even integers, and their sum is even. That's what the statement is saying. The sum of two even integers is even. If x and y are even integers, then x plus y is even. So when you go to prove something, your first goal is to take whatever the statement is and try to break it up into an if-then statement. You with me so far? So step one, think about this way. Now, when you have in an if-then statement, we call the if part the condition, and the then part the conclusion. So when you start your proof, your first line of your proof is going to be let this, assume this. So the first line of our proof is going to be let x and y be even integers. The last line of your proof is going to be this. Therefore, this. Therefore, x plus y is even. So assume our condition is true is the first line of your proof. Therefore, our conclusion is true is the last line of your proof. So I'm trying to give you an outline of how to systematically go about proving things. Step one, break this up into an if-then statement. First line of your proof is let the condition of the if be true. Conclusion of your proof, last line of your proof is therefore the conclusion is true. That's the second step. The third step we call unraveling definitions. It means rewrite this line, plugging in what you know the definitions are. So I said let x and y be even integers. What's the definition of even?
Divisible by 2.
Divisible by 2. So then, 2 divides x, or x is divisible by 2, and 2 divides y, or y is divisible by 2, right? Are there still more definitions that we can plug in? What's the definition of 2 divides x?
Divisible.
There's a number 2 times x equals x.
Right. If 2 divides a number, for example, 2 divides 8, then that means there exists some integer, namely 4, such that 2 times 4 equals 8. You remember our definition of divisible?
Right.
Okay, so since 2 divides x, then there is an integer, then there exists a in z. Z is the set of all integers. A is just an element out there. Then there exists an integer, call it a, such that x equals 2a. So if 2 divides x, then there is an integer, call it a, such that x equals 2a. That's what it means for 2 to divide x. Does that make sense? Same thing with y. Since 2 divides y, then there exists an integer b such that y equals 2b. Now, where did I get a and b?
You just bolt them.
They're just variables. I'm just naming the integer.
Right.
Right? So we're not talking about a specific number. I don't want you to get lost in that. So here you would kind of maybe get stuck from here on out. Here we've unraveled all the definitions. So we know that because x is even, I can write x equals 2a. And we know that since y is even, I can write y equals 2a, or 2b. And then you might be stuck at this point in the proof. So once you unravel from top down all your definitions, the next step is to go to the bottom and unravel your definitions going up. Okay? So, if x plus y is even, what does that mean?
X and y are both divisible by 2.
That 2 divides x plus y. Not that x and y are both divisible by 2. Let me give you an example. Is 1 plus 3 even?
Yeah.
Does 2 divide 1?
No.
Does 2 divide 3?
No.
So you gotta be careful. X x plus y together is an integer. It's an integer, x plus y. Don't let the fact that I use x plus y to represent it instead of c to represent it confuse you.
Right.
That's still just an integer, x plus y, an integer, right there. So 2 divides that integer, x plus y. That's what it means for x plus y to be even, right? And then if 2 divides x plus y, what does that mean? That means that there exists some c, some integer c, such that 2c equals x plus y, right?
Right.
Okay, so going from the bottom up, unraveling definitions get you to 7. Going from the top down, unraveling definitions get you to 4. Now the goal is to connect 7 and 4. Here's where you're kind of on your own. There's no standard method to connect these two things. Now you might look at line 7 and notice that it's talking about x plus y. And you might notice at 4, you have what x is and you have what y is, right? So a natural step of 5 is to add x and y together and see what they are. Remember where you're trying to get. You're trying to get that x plus y is divisible, or x plus y is even. So we need to talk about x plus y, and the only way to get x plus y is to now add them together. So we use our definitions, we know exactly now what x is, and we know exactly what y is. X is 2 times an integer, y is 2 times an integer. So then x plus y equals 2 times an integer plus 2 times an integer, right? We can factor out that integer, so we have 2 times an integer. Now we need the c that we use down here. Let c equal a plus b, so x plus y equals 2 times c. And there exists an integer c, such that 2c equals x plus y, and then 2 divides x plus y. Therefore, x plus y is even.
So, you have to assume that the conclusion is true to finish the proof.
We never assumed that the conclusion was true. Here's what we did assume. That the conclusion was provable.
Oh.
When I put, therefore, x plus y is even, I assumed that when I was asked to prove this, it was possible to prove it.
Okay.
But we never used the fact that x plus y is even in our proof here.
Yeah.
Right? We said, if I'm going to prove this, I'm going to have to prove this. And if I'm going to prove this, I'm going to have to prove this. And then we got to here. And once we got to here, we instantly get that, then we get that. So this is what's called a direct proof, and this is the general way that you go about it. Step 1, convert your statement into an if-then statement. Step 2, make the first line of your proof to assume the condition of the if-then statement. Make the last line of your proof to conclude the conclusion of your if-then statement. Then unravel definitions, top to bottom, and bottom to top. And then filling in the middle is all you. There's no surefire way to get from this point to this point. You just got to figure it out. In this case, you had a big hint that this was talking about x plus y, and you knew what x plus y was up here. Common idea? Let's try adding them together, see what happens. Does that make sense? So that's the best that we can do as far as a general formula for how to go about proving, but once again, there's no surefire way. And that's just for a direct proof. So let's try another proof to get another feel for it. Ignore this for now. That's just because I ran that space over here. So let's try another proof. So proof, let a, b, and c be integers. Then, if a divides b and b divides c, then a divides c. Maybe get rid of that then there. That might be confusing. We'll just put big if. If a divides b and b divides c, then a divides c. You with me? So we need to break that down into an if-then statement altogether. So how do we break that down into an if-then statement altogether? We say, if a, b, and c are integers such that a divides b and b divides c. You see all that?
Yeah.
Then a divides c. So notice my first line.
Okay, but hang on. Wouldn't that already be the if-then statement, and that's just our given? Have you ever taught givens?
So,
That's what I
and
was
if you're comfortable with that, go ahead and do it that way. I'm fine with you doing that.
Okay.
But I don't want to use givens until comfortable with proof in general.
Okay.
So, convert the proof to an if-then statement. Convert the statement to an if-then statement. And then the condition, the if part, if a, b, and c are integers such that a, divides b, and b divides c, that's what we're going to say here. One, let A, B, and C be integers such that A divides B and B divides C, right? That's the condition. Conclusion, therefore A divides C. Okay? First line and last line. Now go back to our first line, that's this one, and unravel definitions. What does it mean for A to divide B and what does it mean for B to divide C? Well, since A divides B, then there must exist some integer, I'm going to call it x, such that AX equals B, right? If A divides B, then A times something equals B. I'm calling that something x. Good? Same thing with B dividing C. Since B divides C, then there exists some integer, call it y, such that by equals C. Good? Is this notation just way too dense for you?
Kind of, yeah, but.
Well, I mean, I see what you're saying, but I don't know how I would write it myself
Yeah.
in other situations.
Did we not go over those symbols?
Not really.
Oh, we didn't?
Well, we went over the integer symbol. I don't know what the E and the other one is.
Sorry. Okay. You guys gotta stop me when I use notation that you haven't seen, because it's just such common notation, it's hard for me to remember where it came from when I learned it. Do you understand what I'm saying?
Yeah.
So sorry, let's go over those symbols. The author probably doesn't use these symbols, but since the board's full, then since you gotta get comfortable with it anyways, let's just learn it. This symbol, let's go over on. I'm going to do s dot t dot, that's such that.
Right.
I'm going to do backwards e, that is there exists. Good?
Okay.
And then if I have a set with elements in it, 1, 2, 3, and I want to say that something is in that set, I can say that 1 is a member of, or is in that set. 1 is in that set. Remember that Z was a set of all integers, right?
Right.
So if I want to say, grab a random integer, I say A is in Z is the same thing as saying A is an integer. So that means is a member of, that means there exists. Good? So let's go over that one more time to make sure that we see it all. Since A divides B, then there exists, that E, there exists, X in the set of integers, or an integer, such that AX equals B. Is this starting to, maybe we better go back to this
It makes
proof.
sense.
It makes sense.
It does?
Yeah.
Yeah.
Okay. Because I don't want to like hammer the point too much, but I also don't want to brush it under the rug. So, if we're uncomfortable with it, let's make it clear you're uncomfortable with it. And if you're not, then don't let me waste time going over it over and over again. So, let me know when you're ready for me to continue. So y'all seem to be frantically writing.
I just want to remember this.
Yeah, that's fine. That's fine. And I'll always say it.
Right. Yeah.
As I go over
The
it.
way that you say it makes sense.
Yeah. So you'll get used to these symbols pretty quick, I think. It's just when you're first showing them, it's like, you're throwing hieroglyphs and math.
Yeah.
And then if you want to look really cool, you use these symbols a lot so people don't know what you're saying. But it doesn't work so well with most people.
Okay,
are
so I'm going to
students.
say Z is a set of integers.
So when you do a Z with an extra line going that way, that's a set of integers. That's what it's shorthand for. And there's other shorthand notation for special sets that we'll come
Right.
across.
We've seen several of them already.
Oh yeah, like the natural numbers
Half numbers, real numbers.
is that with another one like that.
Yeah.
Real numbers is an R with an extra one.
And there was another one that was it
The rationals, which is a Q
Yeah.
with a sideline.
Yeah.
So common notation for sets, but
Why did they choose those ones for those sets? Do you know?
ultimately it all comes from historical reasons. It's never a particularly great reason. I mean, the language of mathematics is still a language. It's just a well-defined language. So it's like why do we use the words that we use for the meanings that we have? Historical reasons. Like you might have come across E a lot. That's just because Euler's name starts with E.
Oh, that's the reason.
And then some mathematicians who wrote a first textbook on this subject, however they wrote the math, that just became the standard because they were the ones who get to the punch. Alright, so going back to this. So we assume we have three integers, a, b, and c, such that a divides b and b divides c. Since a divides b, that means that since a divides b, then there exists some x in z, some integer x, such that ax equals b. And since b divides c, then there exists some integer y, such that by equals c, right? So that's unraveling definitions, we get to 3. Now let's go down to the bottom. We know, therefore, a divides c, our big conclusion that we're always trying to get to. This is why you don't get any credit, by the way, for getting the right answer on a proof. Writing this at the end of the proof doesn't mean anything.
Right.
It's about the logic you use to get to it. Let's unravel the definition going up. If a divides c, then there exists some integer, I'm going to call it z. There exists z in big Z, such that az equals c, right?
Right.
So, here and here are kind of where we end up. We've got c equals az up here, and we got c equals yb up here.
Oh.
But we've also got b equals ax up here. Right? So I'm going to combine these two statements, writing what c equals. So c equals by equals, using b equals ax, substituting in for that b, c equals by equals axy. Notice my goal is I want an equation that has a and c in it. So combining these two, substituting this into this equation, gives me an equation with c and a in it. Once again, there's no guaranteed way that you can combine these two, but that's the leap that your brain might have taken. You might have said, down here I have an equation with a and c in it. Here I have an equation with c, here I have an equation with a. Is there a way that I can combine those to get a and c together? Here's how you combine them to get a and c together. Right? Do you see the substitution I made?
Yeah.
Yes. ax equals b, by equals c.
Right.
So b equals ax. So axy equals c.
Oh, yeah.
There you go.
Yeah.
So c equals by equals axy. Substituting b. Perfect. Alright, so notice what we have. C equals a times something.
Oh.
So call that something z.
Oh.
Then there exists some integer z such that c equals a times something. Az equals c. Therefore, a divides c. Okay? There's two things I've been assuming here that I probably ought to specify. Assumption 1. An integer times an integer is an integer. You don't have to prove that. It's a rather difficult proof for this level. So we're assuming an integer times an integer is an integer. And we're also going to assume an integer plus an integer is an integer. Okay? So x times y, that's an integer times an integer. That's just an integer itself, the integer x times y. So a times the integer x times y. Good? So we had c equals an integer times an integer, which is exactly what we wanted. Therefore, a divides c. If a times an integer equals c, then a divides c. That's what it means for a to divide c. Good?
Mm-hmm.
Feel like you're kind of feeling like you can start doing some of this on your own?
Well, we did some of this in geometry, but not like on the spotlight, I think.
Who did you take geometry from?
Miss Sophie.
Yeah, you didn't take geometry. I've seen the textbook that she uses, and it's a big heaping pile of garbage.
Why?
And I feel so bad for her. Because you do not walk away from that class with the most fundamental understanding of geometry that you have, which is that you now have a system of mathematics based in 4 things: postulates / axioms, undefined terms, definitions, and theorems. And you don't get that. In fact, I don't even think you end that class realizing what the postulates were that all your reasoning was based in. That textbook has you doing theorems, and then it goes back and says, oh, and by the way, these were the postulates. And then continues on, and it never mentions those postulates again. It's like, all your reasoning is based in those things. How can you introduce them afterwards and say, oh, and by the way, this is what you should have been basing the proofs in? They give you some arbitrary place to start. They say, starting here, try and prove this. And they, like, can you connect the dots real quick? More of a connect the dots real quick in some arbitrary order. Why are you using this to prove this instead of this to prove this? Because that's the way the author organized it. Terrible textbook. It's the worst math textbook I've ever forced myself to read some of. And, well, no, can't do it. I'd love to teach a geometry. I did a geometry class last summer to compensate for kids coming on Masada.
Who did you teach it
My most consistent students were three of my little sisters, Leah, Laura, Emma, Timpson,
I didn't even know you had a class.
my brother James.
He just took it
Yeah.
for fun?
Yeah, everyone who was in that class took it for fun.
That's what I
There was no credit available.
Oh.
There was actually credit available, but I told them that there wasn't, and then at the end of the year they stuck with it. Then I'd say, I can give you credit for this. But I didn't want anyone in my class there just for credit. I wanted to weed them out right out the door.
Speaking of, I need a criteria for my math that you're doing. That we're doing.
You need a what?
A criteria, I don't know like what to do.
You're still gonna try, you're not in another math class?
No.
Okay, we will talk after class.
Okay. I'll come Tuesday nights if you finish it.
I'm busy every night.
You said that you'd stay after for us.
Oh. Yes, Tuesday nights I'm doing this. I don't remember which night's which. I just know I'm now busy every night.
Oh, sucky. Well, not sucky, but cool.
I plan my life that way. I mean, I want to be busy every night.
Okay.
Okay. These are my calculus notes. Those are helpful. No, we're just continuing with proofs.
Yeah.
Sorry, lost track of what I was doing. So we're good with this proof. Alright, let's move on to another proof. Proof. If x is an integer such that x is greater than 1, then x cubed plus 1 is composite. You remember what composite means?
Yes.
What are the two criteria for a composite number?
It's a number that's greater than 1 and less than the number. I don't know.
So,
She's on
well, it's actually can just be one criterion, I guess. So, a number A is composite. If I can find a B such that B is less than A is greater than 1, and B divides A.
Right.
So, if this is true for A and this is true for A,
How do you
then
say
A is
that,
composite. Huh?
How do you say that?
A number A is composite if there exists an integer B such that B is this, 1 is less than B is less than A, and B divides A.
Okay.
Or B is a factor of A is another way you can read that. Okay. So we need to show that this and this is true for some B, where A is x cubed plus 1. You with me?
Okay.
And we're given that x is greater than 1. So, if x is an integer such that x is greater than 1 is our condition, our conclusion is then x cubed plus 1 is composite. So our first line is, let x be an integer such that x is greater than 1. Our last line is, therefore x cubed plus 1 is composite. Now, unraveling definitions here, you kind of get stuck. Because unraveling the definition up this way, we don't know what factors we're going to use.
Yeah.
So, once again, while that was a general outline that works a lot of the time, it's not a surefire method. There is no guaranteed way that you can always follow a pattern of proving, and it's going to walk you through the process of how to construct a proof. There's just no way to do it. But we can look at x cubed plus 1, and we know we've got to get factors of that. So we've got to factor this number. How can we factor x cubed plus 1? X plus 1 times x squared minus x minus 1. Common math theorem. to the n plus 1 is equal to x plus 1 times x to the n minus x to the n minus 1 minus minus 1. Common formula. Do the ends that I'm using not make sense?
The n makes sense, the dot doesn't make sense.
Okay, let's just look at examples instead of the general formula. Let's say I had x to the 4 plus 1. That is equal to x plus 1 times x cubed minus x squared minus x minus 1. If I had x to the 5 plus 1, that's equal to x plus 1. You see the formula?
Yeah, this is like when we did, this is algebra that we did last year.
So in general, it's x to the n plus 1 is equal to x plus 1 times x to the n minus x to the n minus 1
I see.
minus x to the n minus 2 minus however many terms there are all the way down to 1. Or x to the 0. 1 x to 0, same thing. See it? We just prove it real quick while we're here.
Might as well.
So let's prove that this equals this. I'm going to distribute. First I'm going to distribute the x to all these terms. What's x times x to the n?
X to the n plus 1.
That's x to the n plus 1. What's x times
X.
That's x to the n.
x to the n? But it's minus, right?
Right.
What's that times that?
X minus n minus 1.
Minus minus x. Just give you the last term, right? That's distribute the x. Now distribute the 1. 1 times x to the n is positive x to the n. 1 times x to the n to the minus 1 is x to the n minus 1. 1 times x to the minus 2 is plus x to the n minus 2. Plus, and eventually we'll get down to an x, and then plus 1. So when you add all the terms you get from the x with all the terms that you get from the 1, everything cancels except for your x to the n plus 1 and your plus 1. Everything else has duplicate terms.
Why do all your negative terms switch positive when you multiply by 1?
Oh, did I write it backwards? No? I don't think I wrote it backwards. Let's think. I did something wrong.
It would be,
That's a good question. What did I do wrong? I have something weird in my formula.
is it x minus 1?
Ooh, is this supposed to be an alternating sign? Minus, plus. Oh my goodness. Well, let's distribute this out, see if that's right. X times x squared is x cubed. Then we're going to get a positive. No, they can't all be negative because the first term is positive. Has to all be negative. Let's see, does that make sense?
Right, because then they would cancel out.
Yeah, then they would cancel out, but let me make sure that that even comes out correctly. I'm saying that this should be a plus, right? Let's see if that comes out. So x times x squared is x cubed. Let's just write it all out to make sure we don't make any small mistakes. So we're doing x plus 1 times x squared minus x plus 1, right? Factoring out my x, I get x cubed minus x squared plus x. Factoring out my 1, I get positive x squared minus x plus 1. There we go. So it should be alternating.
Yeah, it says plus.
Add those together, you get x cubed plus 1. My bad. So this should be alternating. Negative, positive, positive.
Alternating means that. Right?
Alright. So, anyways, back to here. So we've got our condition, and we've got our conclusion. We wrote the first line and the last line, and then unraveling definitions doesn't really help us here. But we do know that we need to factor this thing. And this is a common factoring. You might have had to play around with that to try and figure out how to factor that. Once again, I don't know of any surefire way for factoring things. You just get familiar with common factorizations. So since x cubed plus 1 is equal to that, then this divides that and this divides that. You see that?
Yeah.
This times an integer, namely that, equals this. So this divides this. And then this times an integer, namely this, equals that. So this divides that. Now, which of those two terms would you rather work with?
The first.
Probably the x plus 1. Looks simpler. I agree. So that's what I want to work with. So then, x plus 1 divides x cubed plus 1. Okay? So we found some factor that divides this thing. We found a b that divides that thing. The second question is b greater than 1 and less than the number we're talking about. So it remains to show that 1 is less than x plus 1 is less than x cubed plus 1. Right? That's the second thing we need to show. We found something that divides our number. Now we need to show that whatever that factor is between our number and between 1. That's what it means to be composite, right? Okay, so let's do that. First, let's show that it's greater than 1. And then we'll show that it's less than x cubed plus 1. You with me? So first we're going to show that part of the inequality. And then we're going to show that part of the inequality. Okay? So let's start with showing that x plus 1 is greater than 1. Well, since x is greater than 1, that was given. If x is an integer such that x is greater than 1, let x be an integer such that x is greater than 1. So it's already given that x is greater than 1. So come back down here. Since x is greater than 1, then we know that x plus 1 is greater than 2, adding 1 to both sides. If x is greater than 1, then x plus 1 is greater than 2, adding 1 to both sides, right? And 2 is greater than 1. So x plus 1 is greater than 2 is greater than 1, therefore x plus 1 is greater than 1. You good up to here?
Yeah.
See it? Okay. Once again, since 1 is less than x, or x is greater than 1, we can write that either way. But I'm now doing this part of the equality, so I'm going to write my symbols that way. See what I mean? So since x is greater than 1, or 1 is less than x, then we can multiply both sides by x, and the inequality is still true, since x is a positive number. X is greater than 1. If you have an inequality, multiply both sides by a positive number, the inequality is still true, right? Right. So, since 1's less than x, then x is less than x squared. Multiplying both sides by x. Good? So we have x squared is greater than x, and x is greater than 1. Or in other words, x squared is greater than 1. You get up to here? X squared is greater than x, and x is greater than 1. Therefore, x squared is greater than 1. Get up to there. So since x squared is greater than 1, multiply both sides by x again, and you get x is greater than x cubed. Or sorry, x is less than x cubed. Finally, add 1 to both sides. So since x is less than x cubed, then x plus 1 is less than x cubed plus 1. Like we were trying to show. You losing track of what we were after?
No, that makes sense.
So we're done. So we found a number, namely x plus 1, that divides this, and x plus 1 was between 1 and x cubed plus 1. Therefore, x cubed plus 1 is composite. Should we go over that proof big picture one more time?
Yeah.
All right. From the top. So we want to know if x is an integer such that x is greater than 1. We want to show that if x is an integer such that x is greater than 1, then x cubed plus 1 is composite. Now to show that x cubed plus 1 is composite, we need to find a factor of this and show that factor is between 1 and this number. Okay? So step 1, find a factor. Well, step 1, give us our givens. Let x be an integer such that x is greater than 1. Okay. Now we need to find a factor of this thing. Since x cubed plus 1 equals this, these are both factors, right? So we found the two factors. We could have used either of these in our proof. This one's just easier to work with, so we chose this one.
How would you use the other one?
You'd have to have a different set of proof showing your inequalities. It's just messier because there's more stuff that you got to deal with.
Okay, hang on. How do you factor x cubed plus 1 equals that?
How do I get from here to here?
Yeah.
Saying that this equality holds. Well, you can reverse the steps to see that's true.
Right, but how
But
do you
in general, I was thinking about this formula.
Right, so not thinking about that. Getting the minds of an 11th grader here. You see that? How would you get to there? Because I
Start
would factor
guessing.
it out as.
So what was it? X cubed plus 1.
Isn't there something like dividing, oh yeah, it's dividing polynomials.
Dividing polynomials. So x cubed can be rewritten as x cubed plus 0, x squared plus 0x plus 1.
Right.
Same way as numbers. And then I should know right out the door x doesn't go into that thing. Right?
Because there's one.
Obviously, you can't factor an x out of this.
Right.
Okay.
So maybe you can do an x minus 1 or an x plus 1. Right?
Right.
So we'll guess, I don't know, x plus 1. Okay? How many times does x go into x cubed?
3 times.
X squared times. X squared times that is x cubed plus x squared minus, which makes that a minus. Bring it down, we get negative x squared. How many times does x go into negative x squared? Minus x times. Oh, bring down our 0x over here, sorry. So then, negative x times x plus 1 gives us negative x squared minus x. We're going to take away, so that becomes a positive positive. Bring it down, we get just the x. Bring down the plus 1. How many times does x plus 1 go into that? Plus 1 times. Oh, what do you know? X cubed plus 1 divided by x plus 1 gives us this. So it factors into this times this.
Right.
So that's a way that you can start testing factoring. Alright. Where were we? Okay. So we factor this into two factors. Pick one of its factors, and we need to show that one of its factors is between 1 and the number itself. I choose x plus 1. So I have x plus 1 as a factor of that thing. Now I need to show this. 1 is less than x plus 1 is less than x cubed plus 1. The information I have to work with is that x is greater than 1. So that's the information I'm going to use to prove that 1 is less than x plus 1 is less than x cubed plus 1. So since x is greater than 1, then x plus 1 is greater than 2 if you add 1 to both sides. And 2 is greater than 1. So x plus 1 is greater than 2 is greater than 1 means that x plus 1 is greater than 1. So that shows the first half of the inequality. We showed that half. We showed 1 is less than x plus 1. Now we need to show that x plus 1 is less than x cubed plus 1. And you might look at this, and my brain, when I see this, I say showing that x is less than x, or x plus 1 is less than x cubed plus 1, is the same thing as showing x is less than x cubed, is the same thing as showing 1 is less than x squared. I like undo the operations in my head. Do you see what I'm saying?
Do you think there could be another way to prove that rather than, other than what we did? Saying, like if x is positive, then x cubed is going to be.
There are other ways that you can prove this.
Right.
Yes.
Okay.
Another way that you could prove it is by induction, which we'll learn about. But so I see that I need to show that x cubed plus 1 is greater than x plus 1. What my brain instantly does is says, well, that's the same thing as showing x is less than x cubed is the same as showing 1 is less than x squared. Right?
You're just taking out an x.
Yeah, just reducing it. This is the simplest form of this same information. So I need to get this somehow, and the information I have to work with is that 1 is less than x. Here's what I have to work with, here's where I need to get.
So we just multiply by x.
Yeah, so I multiply both sides by x, which gives me x is less than x squared, right? But I also knew that 1 is less than x. So take this, multiply both sides by x, gives me that, but I still know that x is greater than 1. So 1 is less than x squared. If 1 is less than x squared, x is less than x cubed, x plus 1 is less than x cubed plus 1. So that's exactly what I do. Since 1 is less than x, multiply both sides by x, gives me x is less than x squared, right? And so if 1 is less than x, and x is less than x squared, then 1 is less than x squared, right? So, since 1 is less than x squared, then multiply both sides by x again, x is less than x cubed.
So 1 is less than x cubed.
X is less than x cubed.
Right, but if 1 is less than x, then I'm saying,
Right,
I'm just thinking, other things in place. Then also 1 is less than x cubed.
Yeah, but what we
But
need
it's
is
not-
x is less than x cubed.
Right.
That's the step we're trying to get to.
Right.
So then x is less than x cubed. Since x is less than x cubed, add 1 to both sides, and x plus 1 is less than x cubed plus 1. And we're done.
Yeah.
That's nasty.
It's not.
I don't
Really
like
not.
it. I don't like it.
You didn't thought that. Everyone does. Just takes getting used to, takes practice. They're fun problems to solve. It's nothing better than doing a good proof.
It's just, yeah, it's way, it'll take some getting used to.
Oh, it takes a lot to get used to.
Yeah.
You'll go through this class and you'll still, when people ask you, you comfortable with proofs, you'll say no. Even if you've taken 2 geometry classes before now.
So when do you get used to proofs?
When do you get used to proofs?
Are you used to them?
Oh, absolutely. Very comfortable proving. Proofs are my favorite types of math problems to solve.
Really?
Yes. Because they challenge your mind the most. Anyone can use a formula. Take something to prove a formula. I don't know when you get used to them. I'm trying to think when I got used to them. The way it typically works is, when you're required to do this level, the previous level, you get comfortable with.
Right.
It's like when you get real comfortable with algebra. Well, when you took that trig class and you just had to use algebra left and right. Or, you don't know, can't use calculus as an example. But when I got really comfortable with calculus is when I took physics 2. Electricity and magnetism. That's when I got really comfortable with calculus. Because left and right, just using it over and over again. And the small calculus problems that used to be tough, that became real easy in the context of the problem I'm solving. Anyways, so that's that. Let's move on to another one. Now, this one is going to introduce how we prove if and only if statements. So all the statements we've been proving so far have been implications. A implies B. If A, then B. Now we need to show an if and only if statement. We need to show a statement that says A implies B and B implies A. So, the way we break these statements up, or the way we prove these if and only if proofs, is we kind of break them up into 2 separate proofs. We prove first A implies B, and then we prove B implies A. And then we've shown that A implies B and B implies A. So proving an if and only if statement is almost identical to just proving 2 regular if-then statements. Does that make sense? So let's see it in action. Let x be an integer. Then x is even if and only if x plus 1 is odd. Have I gone over with you guys the double if?
Yeah.
If and only if. So what is this statement logically equivalent to? It's logically equivalent to if x is even, then x plus 1 is odd. And if x plus 1 is odd, then x is even. That's what it's saying. X is even if and only if x plus 1 is odd. So x is even implies x plus 1 is odd, and x plus 1 is odd implies x is even. And so you can think about this half implies this half, and this half implies this half. Okay? So the way that we break these proofs up, we typically have arrows on the outside to say which direction we're proving. So first I'm going to show that if x is an even, then x plus 1 is odd. And then I'm going to show going this way, if x plus 1 is odd, then x is even. And that's big picture how I'm going to go over it. With me? You are? I hope so. Alright, so let's start by showing that x is even implies x plus 1 is odd. And set it up exactly how you would. First line, make our assumption. Let x be an even integer. Let x be an integer where x is even. Let x be an even integer. And then the last line, therefore x plus 1 is odd. Unravel definitions. What does it mean for x to be even? If x is even, then 2 divides x. If 2 divides x, then there exists an integer, call it a, such that x equals 2a. Right? And now let's go back to the bottom. Therefore x plus 1 is odd. What does it mean for x plus 1 to be odd? That means x plus 1 can be written as 2a plus 1. Now connect the middle. Oh wait, there is no middle.
Yeah, that's it.
We're done. That's as easy as it gets.
Yeah.
You follow that?
And that's just because the definition of odd is that, right?
Yeah, the definition of a number being odd is it can be written as 2 times an integer plus 1.
It's,
You don't remember that definition
No,
from last time?
I didn't mind the simple one saying.
Okay. You remember the definition of odd?
Yeah.
Yeah. Even, divisible, prime.
Composite.
Alright. Okay, let's do it the other way. And it's just as easy. So this time we're going to show that if x plus 1 is an odd integer, then x is an even integer. First line. Let x plus 1 be an odd integer. Last line. Therefore x is an even integer. Unravel definitions. If x plus 1 is an odd integer, that means that there exists some a and z such that x plus 1 equals 2a plus 1. That's what it means for x plus 1 to be odd. Right? Go back to the bottom. X is even. What does it mean for x to be even? 2 divides x. What does it mean for 2 divide x? There is some integer a such that x equals 2a. We're done. You might need to make a leap in your head. If x plus 1 equals 2a plus 1, then x equals 2a. You got to make sure you can make that connection. It's difficult, so put a big sign up proving it. Good?
Yeah.
Applause. That's very standard in my classes after proof, in case you guys are wondering. You've been really weirded out about applauding when I prove things. It's awkward. Okay. Don't really. In case you take me serious. Next proof. The point of this proof is to teach you to reference previous proofs. Never, 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 ever do you need to prove the same thing more than once. If you've already done it somewhere, reference the proof. Now I haven't been naming these proofs as they come up in your book, but they're named in your book. They're Proposition 5.1, Proposition 5.2, Proposition 5.3. So for example, this proof was Proposition 5.3. Okay? So I'm going to use this proof in my proof here. What does this proof say? Let A, B, C, and D be integers. If A divides B, and B divides C, and C divides D, then A divides D. Let's look at this proposition real quick.
It's basically
Let A, B, and C be integers. If A divides B and B divides C, then A divides C. See how that statement and that statement are really close?
Yeah.
This just has the D and we're proving A divides D instead. Okay? And it's really just using that to
That's what I
advise.
love about proofs, I think.
Yeah, it's wonderful. You start referencing what you've already used. We're building up a framework of tools that we can use.
Right.
So, let A, B, C, and D in Z, or in other words, let A, B, C, and D be integers, such that A divides B, B divides C, and C divides D. Since A divides B and B divides C, then by Proposition 5.3, A divides C. That's what we showed.
Right.
If A divides that, and the number it divides some other number, A divides that number. If A divides B and B divides C, A divides C. Once again, we're going to use it again. Since A divides C and C divides D, then by Proposition 5.3, A divides D. We're done. Now, you could have done this a long way. You could have unraveled definitions and multiplied all the numbers together, and that's perfectly fine, and you would have been able to prove it.
It's easier.
Maybe. It has less writing. Easier is a hard thing to say, because some people have a hard time referencing some other theorem than they do just reproving it. So, in my book it's easier, but there may be some book out there where it's not easier. I don't know. And then the last proof of this, when we're doing mathematical equations, a lot of times we forego a lot of the verbiage. Like when you're using the associative principle or the commutative principle or whatever, you kind of just keep writing it out. So let's see an example of something like that. If x is greater than 2, then x squared is greater than x plus 1, is what we're going to prove. With me? So, let x be greater than 2. Then multiply both sides by x. X squared is greater than 2x. 2x can be rewritten as x plus x. We already know that x is greater than 2, so x plus x is greater than x plus 2. And we know that 2 is greater than 1, so x plus 2 is greater than x plus 1. Therefore, x squared is greater than x plus 1.
Can't you just...
And it's also common when you're doing proofs, if you keep referencing the same equation over and over again and you're kind of manipulating it, that you don't take a bunch of space to do that and write out what you're doing. It's more, I don't mean not a bunch of space, but I mean not much right. So if I have 2x squared, well, let's pretend I was doing a proof, saying prove y equals something. So if I have 2y plus 4x plus 8, and I'm trying to prove equals 0, and I'm trying to prove that y equals minus 2x minus 4. So I'm given this and they say prove this. Then rather than being verbose in all our writing, we just go straight down and keep writing the same equation the same way you did in algebra class. So I then write 2y is equal to negative 4x minus 8, y is equal to negative 2x minus 4. And call it. So when you're doing math, you can kind of just keep going. It's just algebra manipulations like we did right here. We're right here going sideways or down, however you want to do it. You don't need to specify what you're doing each step of the way. Just do it. This isn't a class that's proving how to do these algebra operations, so you don't need to specify. Does that make sense? All right. So that was chapter 5, which was the main chapter. Chapter 6 is called a proof by contradiction. This is how you prove a statement is false.
Disprove something.
Or disprove some statement. So I make the statement, all integers are even. How do you prove me wrong?
You show that.
Give an example of an odd.
You say negative 1 is odd and negative 1 is an integer. Or 1 is odd and 1 is an integer. Or whatever number you choose. Right? So that is the way proof by contradiction works. You look for an example where the statement doesn't hold, and that proves the statement false. That proves the statement is not true. Does that make sense? So, let's find a statement for you guys to disprove.
Okay, so I have a question. Next week we're taking chapter 1 test.
Yes, next
In
Tuesday.
class.
In class.
It's not homework.
It's not homework.
Okay, so it's this test right here, right?
What do you mean by this test?
I'm on the book.
No. So
You're gonna give it to us?
the problems for the test will come from either your homework or that chapter review. Those are the two places I pull test questions from.
Okay.
So it'll either be homework problems that you actually solved, they were assigned homework problems, not any homework, but homework problems I actually assigned to you, or those questions. That's where I pulled my test questions from. Good? Alright. Counterexample. Proof by counterexample. Disprove this statement. Yeah. If A and B are, if A and B are integers such that A divides B and B divides A, comma, then A equals B. Prove me wrong.
Can you just put in numbers for those?
Yeah, if you can find one example where it's not true, then you're done. So be thinking about that, and I'll start moving on to Boolean algebra.
Is that 7?
Yeah, this is all of 6.
What is Boolean algebra?
Don't worry about it. Focus on this problem.
Okay. So I'm just like, do it?
Yeah, see if you can figure it out. Don't tell people when you figure it out
Well, if all you have to do is find one example of it.
where it doesn't work.
Right.
So you're saying this statement, I'm saying prove that this statement is not true. So see if you can come up with a case where it doesn't work.
Okay.
See if you can find A and B such that that statement's not true. I'll give you a hint. Don't pick the same number for A and B, otherwise it's going to be true.
That's about it.
You're welcome.
Wait. Okay, so that's true?
No, it's not true.
You're proving it wrong.
Prove that's not true is what I'm saying. Find a counterexample.
Wait, what? I'm confused.
This statement, if A and B are integers such that A divides B and B divides A, then A equals B is not a true statement. I'm telling you it's not a true statement.
Okay.
So find an
If
example.
A is true, they're saying, okay, this is true, now disprove.
No, they're saying, let's say that you are a mathematician and your job is to check people's theorems. And someone comes along to you and they say, hey, I proved this. And you can come up and say, actually, you didn't prove that because it's not true. Here's an example.
So what we need to find is two numbers that can divide each other that aren't equal?
Yes, you need to find two integers that A divides B and B divides A, but they're not the same integer.
Okay.
Okay.
And it's possible?
And it's possible.
That doesn't make sense.
It does, I promise. You just don't know how.
Oh, really?
Yes, ma'am.
And it can't be like fractions?
You can use whatever you want, but integers is what we're looking for, so I'm going to stick with those.
Doesn't matter whether or not it goes into the negative or, so if I
Is
divide
it negative
a
an
positive,
integer?
if I divide a negative into a positive, it'll give me the same answer, it'll just be either positive or negative.
Is a negative, are there negative integers?
Yes.
Then you can use negative numbers. You can also use 0.
Okay, got it.
Great. Do you all have it? Anyone not have it? Let's ask it that way.
I think I have it.
What do you have?
Well, I'm trying to think of an integer that, where it divides to be an integer.
Have you come up with an A and a B? Can you tell me two integers, A and B?
Yeah, I have one.
What do you have?
-2 and +2.
There you go. Pick a number, take the negative of it, the positive of it, boom, you're done.
Yep.
So -2 divides 2, and 2 divides -2. Obviously, 2 is not equal to -2. Alright, now we're on to Boolean algebra. Boolean algebra we already covered because when I cover logic, I cover Boolean algebra. Boolean algebra is thinking about that symbol for not, that symbol for and, that symbol for or.
Okay, hang on. So for these, then you would just write the sentence, or just write the one condition, or do you have to like set it up like that?
You could just say oops.
Okay.
There you go. It's proof. Alright. Moving on to back to logic. So we talked about the not operator. And we said not true is false, and not false is true. Right? And true and true is true. True and false is false. False and true is false. False and false is false. Or, rather than sitting here doing these tables all over again, let me just do A or B right here. So this was or is this symbol. A or B. If A is true and B is true, A or B is
True.
true. Right? If A is true and B is false,
True.
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 False.
True.
Yeah.
Or means at least one of them is true. False. And then implies was the hard one. I'll be very happy if you guys get this right.
True.
True implies true is
True.
okay. I didn't want to yell. True implies false is
False. False.
Rude.
False. False.
if true, then false is false. False implies true is
True. False. True.
false implies true is.
True. False.
True.
Let's set it up. A is I'm holding a marker. B is I'm holding an eraser. Let's set this case.
Oh, wait, no.
If I'm holding a marker, then I'm holding an eraser. Is the statement false?
No, it's not.
Then it's true.
Okay.
It's great. You'll get stuck on it tons of times. And false implies false is
True.
true. True. True. Okay. So those are the basic operators. Now they're going to give you big old expressions, Boolean expressions, and have you simplify them. The same way that I might come along and I might say, hey, what's 3 plus 2 times 4 plus 7? And make some poor kid go through all that in 2nd grade. We're going to do that to you. We're going to come along and say, what is true and true, or false implies true equal? Let's go through it. True and true is
True.
true, so that simplifies to just true. So true or false implies true. Let's keep working with it. Should have put parentheses like that. Sorry. Let's continue working with it. So now we just have the true in there by itself, so we don't need those parentheses. True or false is
True.
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 So that's true.
So true implies true, and that is
True.
true.
Huh.
So that whole statement evaluates a true. This is called Boolean algebra,
Interesting.
where all we're doing algebra on is Booleans.
Is that what they're called?
Booleans are true or false values. Yeah.
Pretty cool.
So the same way that an integer, or the integers is a set of all the integers, the Booleans is the set alt true. That's the set of Booleans. So Boolean variables means it's one of those two things. And you use these operations the same way that you use plus, minus, and times and divide and whatever. So there was a quick example. Now we'll do the ones that the author actually wants to do.
True and false is false.
True and false is false.
Yeah.
True and false is false. True is only true if both statements are true. Right?
Right.
So let's set up A is I'm holding a marker, B is I'm holding an eraser.
Right.
I'm holding a marker and I'm holding an eraser. No, I'm not.
Oh.
Right? There we go. Setting up a concrete case often makes it just click like that.
Okay.
Right there. So let's see. Not x and y is not x or not y. That's a good one. Distributing not over and. So let's figure out what. Or here's what it wants us to do. It wants us to prove that not x and y is logically equivalent to, equals, or is logically equivalent to, doing the arrow back and forth, not x or not y.
Isn't it and?
No, it's or.
Oh, yeah, okay.
So, let's prove that. Get rid of all this. We know the basic operators. So the way that we prove these is with truth tables. You show that regardless of what values you plug in for this and what values you plug in for this, they always give the same thing. That's how you do it. Right? And what are all the possible values I can plug into that for x and y? I could have x true, y false, x false, y true, x false, y false. These are all the possible things I can plug in for the values here and evaluate it, right? So, here we need to evaluate not x and y, and here we need to evaluate not x or not y. You understand what we're doing?
Yeah.
You understand how we're going to fill in the table? Let's go. All right. So, looking at this case, true and true is?
True.
Not true is?
False.
False.
Oh.
So when you plug true and true in there, you get false, right?
Mhm.
All right. Plug true and false in there,
False.
you get false.
Which is
Not it, which is true.
Right.
All right, do this one in your head. True?
True.
All right. Do this one.
Sure.
All right. So that's what we got when we plugged in all our values here. Now let's plug them all in here and see if we get the exact same things for every combination. Okay? So, false or false is false. Okay? Now in this case,
False is true.
True is true.
True is true.
It's true.
True is true.
and lo and behold, they get the exact same things in every combination. So no matter what values x and y you pick, these two things give the exact same value. That's what we mean by logically equivalent. That make sense? So when they ask you to prove something like this, prove that this is logically equivalent to this, you just do a truth table. Don't write out an essay explaining it. Just write the truth table and you're done. This is self-explanatory enough. Okay? Keep going back to my red notebook. And maybe we'll just list these out. We don't need to prove them. You know how you would prove them. So you can just take my word for it that they're true, or you can go home and check it yourself. But I'm not going to write out the truth tables for the list of things I'm about to say are true. So Boolean algebra satisfies some set of properties really close to properties that you've seen for numbers. So one is and or are commutative properties. What do I mean? I mean x and y is the same thing as y and x, and x or y is the same thing as y or x. What we mean by that is and or are commutative, the same way that multiplication is commutative and addition is commutative. These are properties that Boolean algebra has, just like the real number algebra has certain properties with its plus and its times. And then the not in this context is very similar to negative in algebra. So let's look at the next one. The next one is the associativity law. So x and y and z is equal to x and y and z. Similarly, that's like that, x or y or z is equal to x or y or z. Once again, you prove all these things just with truth tables. It's just that when you have 3 variables and you have to do a truth table with 8 columns and control A. So I'll probably just make you prove these on your test so I don't have to do it and you can see it. Okay, and then we have our identity element. What is any number times 1? It's just that number, right?
Oh, yeah.
In similar fashion, x and true is always x. True is the and identity element.
Huh. That's interesting.
Or also has an identity element, and it's false. X or false is just whatever x is. That's its identity element. The same way that 0 is an identity element for addition.
So, could you say that x and false is not x?
X and false is a lot like x times 0.
Oh, you're right. Okay.
The same way that x times 0 equals x, we have x and false equals false.
Right.
Or it's equals 0.
Equals 0.
The identity element. That gives you the identity element, just like that gives you the identity element. And similarly, the same way that, well, no, never mind. Okay. 4. The next property that this pulling algebra satisfies. Not x equal to x. X and x is equal to x. X or x is equal to x. Good? If any of these seem particularly strange to you, we can prove it. If any of them aren't obvious. Distributive property. X and y or z is equal to x and y or x and z. Similarly, x or y and z is equal to x or y and x or z. Seven. X and not x is always equal to false, and x or not x is always equal to true. And then the last one is the one that we just proved, how you distribute a negative or a not. Not x and y is equal to not x or not y. And similarly, not x or y is equal to not x and not y. I don't know. And then start going through examples of it.
Can we do number 6?
So, try and logic, just think about it for a second when you hear the words, and I think you'll quicken your brain. So if you have x and y or z, then you either have x and y, or you have x and z. So think about it. You go and you purchase a burger. X is you get a burger, and you can get a Coke or a Pepsi. So here's your option of food. You only have one option for food, but you have two options for your drink, this or this.
Okay.
So you either have your sandwich and your Coke, or you have your sandwich and your Pepsi.
Oh.
Does that help?
It's like
Yeah.
distributive property.
Really helpful.
It is. It is called the distributive property on Boolean algebra.
Okay.
It makes sense. I mean, I get it. It's just.
No, it's weird. It's just a lot of symbols and anding and oring, and you're like, whoa, back up.
Yep.
But I sometimes just like using the language you're already comfortable with is enough to capture the idea for you, and you don't need to write out a full truth table.
So
But if we need a full truth table, we can.
when you multiply, like, it's not really multiplying them. So you just gotta think of that.
Yeah, it's not multiply, it's and or.
Right.
It's not times and plus, it's and or. Different operations. They're just similar.
So weird.
Because this is developing algebra on Booleans as opposed to developing the algebra on the real numbers.
Yeah.
Okay, you erase
Well, I don't need to erase it. I just want to make sure each one makes sense. Let's just go over it one at a time, make sure it makes
Are
sense.
all of those in the book or during the test?
They're all in the book.
Okay.
But let's make sure that all of these are built through your intuition. So first one, x and y is the same thing as y and x. That one should make great sense, right?
Yeah, that makes sense.
X or y is the same thing as y or x. That should make great sense.
Okay.
Okay? What about this one? X and y and z is the same thing as x and y and z. The only time those are true is when x, y, and z is true. The only time this is true is when x, y, and z is true. All other cases, the whole thing's false. That make sense? Similarly here, if any of them, the three is true, doesn't matter which side you look at, the whole thing's true. So the only time this is false is when all three of them are false. The only time this one is false is when all three of them are false. You see that? Okay, that takes care of that one. This one, x and true is just going to be whatever x is. If x is true, then true and true is true. If x is false, then false and true is false. So this spits out whatever value x is. Similarly, this spits out whatever value x is. If x is false, false or false is false. If x is true, true or false is true.
Right.
Good? Basically, these are ways that you simplify Boolean expressions. Right? So if I was trying to simplify some expression, I saw x and t in there, I know, just replace that with x, and we're good. Continue.
Hang on, what would that be?
What?
The or, x or, couldn't that be a t or something?
So if I plug in true for x, then true or false is?
Sure.
I'm saying, couldn't that s be a t?
No.
No, because that's always true. That is,
Because if x was
Oh.
t.
Yeah, okay, yeah.
did we not write that?
Now I see what that means.
Yes, we did. Okay. Next one. Not x is x. Right?
It's like negative x.
It's like negative, negative.
Right.
Exactly right. Okay, let's look at this one. X and x, if x is true, then it's true. If x is false, then it's false. So it's just whatever x is. X or x, if x is true, it's true. If x is false, it's false. So it's just whatever x is. This one we talked about the first half. Did you understand this? Do you remember?
Yeah.
Okay, so let's do this one. X or y and z means x or y and x or z. So,
Still makes sense.
let's think about this in terms of chores. Your mom says you can rake the lawn or you can do the dishes and put them away. Okay? What are your options? You can choose between raking the lawn or doing the dishes, and breaking the law or putting the dishes away.
That does not
That
make
doesn't
sense.
make any sense.
Yeah, that was a bad example because in that or, she means the exclusive or. She doesn't care if you do all the jobs. Right? Doing all the jobs still satisfies us, so maybe that's not a good one.
Those aren't your only choices.
Because you're thinking about the or differently.
Yeah, but I kind of see what you're saying.
Let's try it this way. A person in the room is a student, or they're holding a marker and they're holding an eraser. You're a student, or you're holding a marker and you're holding an eraser. It's possible for you to be a student and hold a marker and hold an eraser,
Oh.
right?
Oh, yeah, that's
You can do all of those things,
But you're doing that and one of those.
but in other words, if you're not the student, then it's for sure that you're holding a marker and you're holding an eraser. Because if this is false, this is true, if the whole thing's true, right? So now let's look at it this way. So keep that in mind. You're a student, or you're holding a marker and you're holding an eraser is the same as you're a student, or you're holding a marker, and you're a student, or you're holding an eraser.
Yeah.
You see it? Did that one help?
Yeah.
Should we write out the whole truth table?
Okay, but isn't there one more choice?
So how do you do a truth table with 3 columns? Because we haven't gone over that.
You just need to write down all the combinations. So it has 3 variables, so we have 3 variables. X, we'll just do 1 with 3 since it's probably good to see in general. Let's see, what were we doing? X or Y and Z. Is 1, and then we're going to do X and Y or X
No,
and Z.
you have that switched.
X or Y, thank you. X or Y and X or Z. Right? So now, we need to show that these two things have the same value, no matter what values you choose for X, Y, and Z. That's how we prove that they're the same, right?
Right.
That's terrible. Anyways. So we need to write out all the possible combinations of X, Y, and Z. Okay? The way that you typically do this systematically is start with Z. What are all the possible combinations of Z?
True and false.
True and false. Now, what are all the possible combinations for Y?
True.
True and false. But for each Y, you can have a true and false and Z, right? So I can have Y is true, true and false and Z, or Y is false, true and false and Z, right? Now, I can have this when X is true, and then this again when X is false. So, true, 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 false, 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 and then rewrite that exact same thing again. And then you also notice the pattern. You do half true, half false on this one.
Right.
Then half of each half true, half of each half false. And then half of each of those halves again. And you could also follow that pattern going in. And that will get you every combination. So every combination of true and false is now listed here. Now you just fill it in for each case. When everything's true, what's this statement?
True.
True. When everything's true, what's this statement? True. Alright. So now let's do X and Y is true, Z is false. True or anything is always true, so don't even have to think any further. Right? Because X is true.
Right.
So that's where these little tricks come handy. Now, let's see. Z is the only thing false. Everything else is true. But true or false is
True.
true. This is true. True and true is
True.
true.
Right.
Next one. Y is the only one false. True or anything is still. In fact, let's not waste our time. This statement we know is true every time X is true. Right?
Right.
So let's just finish filling in those 4. And this statement we know is true anytime x is true. Because true or anything makes this true. True or anything makes this true. True and true is true. Good there? Now, if everything is false, we can instantly knock those out, right?
So basically the rest of them.
Well, not the rest of them. But, actually, yeah, we can think about that. No, we still can. So now, when x is false, the statement is true only when this is true. When y and z is true.
Oh,
Right? So now x is false. So the whole thing is true when this is true. When is x and z, y and z true? When both y and z are true.
Right.
So that's true right here. And then everywhere else this one's false. See that? Okay, now let's see if we can come up with a way of capturing the thinking in here. If x is false, then this statement's only true when y is true. This statement's only true when z is true. And the whole and is only true when both those are true. So I only know, so I know that's only true when both of them are true, and then false everywhere else. There we go. So there we go. They have the same values no matter what you plug in. Therefore, they're logically equivalent, and that's how you handle a truth table with 3 variables.
So can you have, like, you can say a moving equation where you can have x and y and z all in parentheses? Like, so where you could have, like, anything wrong with this?
It's like that, like number 2.
I guess that's.
Oh,
like
you're
how
saying do
mine's-
this?
Yeah.
Okay. So you might be tempted to do that because when we do math, sometimes we're right. Right? When we do that, we are being very, very, very lazy. In reality, there is some order. Turns out the order doesn't matter, so we're being very lazy. But if you were to write out math very rigorously, it would always be either this, inside your parentheses, inside the problem, however it is, or it would be, right?
Right. So you just use the distributive property?
Yeah, now those are logically equivalent, and so since we don't care which of those it is, we don't bother writing it. But one of those is happening.
Okay. Yeah, that makes sense.
So you might be lazy and write this, but that's just because it doesn't matter if this is what's happening in the parentheses or this is what's happening in the parentheses. You are doing one operation first. We don't know how to just plus 3 numbers. That doesn't happen. You take 2 numbers and you plus them, and then you plus a result.
Right.
Plus is a binary operation. It takes 2 things. You can't compute this just. Doesn't make sense. We don't have a way of doing that. So you have to handle it 2 at a time.
Okay.
Same thing. Good question. Let's do one more, and then we're done covering material, and then you guys can go on break, and then we'll spend the rest of the day going over problems, getting ready for the test next week, working on homework, whatever you'd like, and I'll also stay after school. So the last one that we're going to show is that, let me kind of set the table as we do this, so I don't have to. I want to show that x implies y is logically equivalent to not x or y. Sorry, not x. Use my little tick mark there. So show that those 2 things are logically equivalent. Because sometimes it's helpful in your proofs to think about it this way instead of this way. Okay? So let's write out all our cases. True, true, false, false, true, false, true, false. We already know an implication is true, false, true, true. So let's look at this one. Right?
Yep.
Alright. So, not true is,
False.
or true is.
True. So anywhere where y is true is true.
Not true is,
False.
or false is.
False.
True.
False or false is false.
Yeah.
And then anywhere y is true, it's true, right? So that gives us a true there. And then finally, plug in false and false. What do you get?
True.
True. And it's logically equivalent.
Here we go.
So if you don't want to think about x implies y to prove something, you can think about not x or y. Is not the condition or the conclusion true? And we'll see examples where we start messing with the logic like that to do things. What we typically do is what's called the contrapositive. Maybe show the contrapositive real quick because we use it so much. And we'll leave that last one. Contrapositive. Sometimes instead of showing that x implies y, it's easier to show that not y implies not x. Okay?
Okay.
So let's write that out. You plug in true and true, what do you get?
False and false.
And false implies false is
True.
true. Alright? Now we plug in false for y and true for x. So false for y makes true. Right?
True implies false equals false.
True implies false equals false. Perfect. Now plug in,
False implies true is true.
yeah, false implies true is true, and then false implies, or true implies true is
hang on.
true.
No. True implies false is false.
But
True implies false, but this is false implies true. So y is true, makes it false.
Wait, what? Oh.
Plug in t, plug in true for y gives f. Plug in f for x gives t. False implies true is true. There we go. So that's the contrapositive. So rather than showing that if A divides B and B divides C, then A divides C, rather than showing that, you might show that if A doesn't divide this, then A doesn't divide B or A doesn't divide C. That doesn't make sense for that one, but it's common proof technique
Okay.
to rethink about your proof that way. The same way that when we were talking about implications, sometimes it's easier to ask, is a statement false than is a statement true? You'll see examples as they come up.
Okay.
But that's called the
Should we start
contrapositive.
at 5.1?
So you can go on break, you can start homework, and you're happy to ask me, you can ask me any questions you would like. 5.1, or chapter 5 is the hardest chapter that we covered. So I would put the majority of your focus on that chapter.
Wait.
You can ask me any questions you want. I'm happy to help with any homework that you want. I strongly recommend reading through all your homework problems real quick, guessing which ones are going to give you the most trouble, and having me help you with those.
Okay.
Well, do you think we could get 1 through 13 done before we leave?
I think I could. I don't know what you can do.
Well, why don't we just watch it?
Because then you don't do the problems. I do them. And I already know I can do problems. And we can stop the recording because I don't think you'll care about anything we cover from here on out.
Prove that the sum of two